Okay, so let's go ahead and get started. Let's see, because of the snow day yesterday, I did get all your tests finished marking. I've gotten here to give back so I can maybe quit class a couple minutes early and give them back to you. The solutions are posted. Of course, you can come ask me about the test, but I would just ask you to look through your tests, look through the solutions, and then come talk to me. So do that first and then come see me. We'll clear up any confusions. Any questions before we get started? Last day we finished up chapter 27. And chapter 27 was all about finding the force on moving charges. And then we saw that that meant we also have magnetic forces on current carrying wires. So today we come to chapter 28, and that comes back to something we said in our first part about magnetic fields, which is that magnetic fields are made one of two ways, either by permanent magnets or by current carrying wires. So those are things we're going to talk about in this chapter, how a moving charge makes a magnetic field. Something that I find really interesting about this, and I think it's sort of just because it goes a little bit with my life, is that this discovery of a magnetic field being made by a moving charge, this was completely serendipitous. So Hans Christian Ørsted, he was a lecturer, not any different from me, and he was giving a class, and he had a class about circuits, so he was talking about current and voltage and all this stuff, and he set up a circuit in class. The serendipitous part was he happened to have a compass next to the circuit, so that was the lucky part. So mine, of course, is artificially set up to work and be a nice demonstration, but here's my compass. I've got it lined up with the loops of wire here. I plug this into the power supply. I expect he had some sort of battery. I'm going to turn the current up, and the compass deflects, right? So you got to think, in the 1800s, they didn't have any idea about this, and he turned on the current, and he saw the compass flip. I'm thinking mind blown right in the middle of class, right? Brand new discovery that hadn't hit the journals. You know, no doubt other people had seen it as well, but he saw it in class and sort of talked about it and learned about it. So I think that's kind of cool. It was just a lucky happenstance that he noticed it and started to think about it. And I guess that's actually what a lot of physics is. People just see stuff and say, hey, that's cool, how does that work? That's kind of the heart of the entire field of physics. So that's the stuff we're going to look at, is what field is made by the charge that's moving or by the current that's flowing through a wire. So Ørsted did discover the fact. Two guys, Biot and Savart, a couple of French guys, they wrote an equation that described the magnetic field made by a moving charge. So the equation that gives the magnetic field created by a charge Q moving with velocity v is that the magnetic field is equal to mu naught divided by 4 pi times the charge Q times v cross r hat divided by r squared. Okay, lots of symbols in there, so let's go through all of them. So first of all, we have a charge Q. We can draw a charge Q. That's down here. I've decided to call it positive. It doesn't have to be positive, but it's either positive or negative. It's moving with some velocity v. I've decided to move that to the right. This equation gives me the magnetic field at some point P. Maybe I'll pick that to be right here. This point P, why don't we go through the symbols one by one? So we've got Q taken care of and V taken care of. We know where we're finding the field. This mu naught is a constant. So epsilon naught was our permittivity of free space. It describes how electric field goes through a vacuum. This one is called the permeability of free space. It describes how magnetic fields go through a vacuum. Okay, so epsilon naught and mu naught are similar. Mu naught has a value of 4 pi times 10 to the minus 7 Teslas times meters divided by amps. If you're using this constant, just be careful with how you do it in your calculator. I recommend, and you're probably going to laugh that I'm explaining it, but it gets people wrong a bunch of times. You do 4 times pi times 1 exponent minus 7. That will do the trick for you. Sometimes people just put things in their calculators funny way and they get wrong answers. So there's something to be aware of. So that's mu naught, that's divided by 4 pi times our charge q. This is the whole charge, be it positive or negative. Okay, so you keep your sign of your charge. V is your velocity vector. Then we're doing the cross product with what we call r hat. So r is a vector that goes from our charge to our point. That's the r vector. So that describes where point P is. The magnitude of r, that's what's in the bottom down here, so that's r squared, so that's the distance squared. This r hat is a unit vector that points in the direction of r. So I hat is a unit vector that points right, j hat is a unit vector that points up, k hat is a unit vector that points out of the page. R hat is a unit vector that points in this direction, away from your charge towards point P. So there's r hat. Because it's a unit vector, it has magnitude of 1, but the same direction of the vector r. So unit vector means magnitude equals 1. Okay, any questions about the equation or the symbols? No, everything's good. So our equation has a cross product in it. It's got V cross r hat. That tells us that our magnetic field B is going to be perpendicular to the velocity, and the magnetic field is going to be perpendicular to that r hat vector. Okay, so our V cross r hat. We can always do the math. We can always do a right-hand rule. So the direction of B is going to be the direction of V cross r hat. We put our thumb in the direction of V, put our index finger in the direction of r hat. We see what our extended middle finger does. It comes out of the page. So the direction of the magnetic field at point P is out of the page. So V cross r hat gives us V. So we can draw that if we wish. So you can always do the cross product to calculate it, or you can do a magnitude and direction. Okay, we're going to deal with magnitude and direction soon. So let's just take a quick bit of practice on the right-hand rule for getting the direction, because we're going to do that a few times as we go through this section. So here's two examples. What is the direction of the magnetic field at our point P right here? So we'll label this our point P. Our velocity is into the page, and our point is over here. So let's see if we can get the direction of that one. So while you were trying it, I just put the vectors on the page there. So your thumb goes with your V, that's into the page or into the screen. Your index finger has to go with your r hat, so I just got to twist myself around a little bit. So my V is into the page, my r hat is this way, and then your extended middle finger shows the direction of the force. Okay, so V cross r hat, V cross r hat gives your force upwards. Oh, direction, I was saying force, I meant magnetic field. Direction of the magnetic field is going to point straight up right there. So our answer is C. So here's another one. I've got a negative charge, it's moving to the left, and we want to find the magnetic field right here at point P. Any takers on which direction this is? So we put our thumb with the velocity vector, and then our index finger has to match r hat. So V cross r hat. So V goes this way, my paper. V goes this way, r hat goes this way. Your extended middle finger goes into the page. Okay, that would be the direction of the magnetic field for a positive charge. That charge is negative. Okay, so this magnetic field must point out of the page. Okay, any questions? If you like the math, you can do the math too, of course. So this Q is negative. V is in the I hat direction to the right. R hat is straight down, that's negative J hat. So negative I cross negative J hat would give you plus K hat. Okay, so if you prefer the math, you can always do the math. Either way is fine. Okay, so let's work on getting some workable forms for that expression for the Biot-Savart law. Particularly if we want to use the magnitude and direction with the right-hand rule. So let's just remember our setup. Our Biot-Savart law is mu naught over 4 pi times q v cross r hat over r squared. Our initial setup we put a positive charge right here. That was q. We said it was moving to the right. That's our velocity vector. We talked about a point P up here, where this is the r vector, and r hat was in that direction. And it gave us a magnetic field that pointed out of the page. Okay, so there's our setup. So if we wanted to do magnitude and direction when we're calculating the magnetic field, we could find the magnitude of the magnetic field, magnitude of B, which we might just call B, is mu naught over 4 pi times the magnitude of the charge Q times the magnitude of V cross r hat, and divide that by r squared. And so if we're finding the magnitude of B, we've got to take the magnitude of the charge, and we have to find the magnitude of this vector product here. So let's deal with V cross r hat next. The magnitude of a cross product, V cross r hat, is the magnitude of V times the magnitude of r hat times the sine of the angle, and that angle is between V and r hat. In our picture here, that would be our angle theta right here. Okay, so always between V and r hat, no matter what angle you're given in a problem to solve. So let's put this up here, and it gives us that the magnitude of the magnetic field is mu naught over 4 pi times the magnitude of charge Q. The magnitude of r hat, remember, that was equal to 1. And the magnitude of a velocity vector, we'll just write as the speed. So mu naught over 4 pi times Q times V times sine theta over r squared. That's how you can find the magnitude of the field, and then you can use your right-hand rule for getting the direction. So that's a good way to do it as well. So, you still good? So when we did electric field, we said that source charges make electric fields, and we mapped out electric field lines. We can do the same thing with magnetic fields, and we can map out the magnetic field lines. So a charge Q moves with a velocity V. We're going to say that this charge Q is moving with a velocity out of the page, so it's coming up this way. Draw the magnetic field around charge Q. So if we want to draw the magnetic field, let's draw it at a few different spots, then let's map it out and we'll get the whole picture. So let's say that we've got our charge here, we'd like to draw our magnetic field right here. So there's our point P. Our vector R goes from the charge to our point P. Our unit vector R hat is in that direction. We use our right-hand rule. V is out of the page, R hat is up, and our magnetic field is going to point towards the left. So the magnetic field at this point looks like this. Okay. So V cross R hat gives us a vector that points to the left. So now let's pick a different spot. Let's come over here. If we wanted to find the magnetic field right here, we'll do the same thing again. Draw the R vector, the R hat vector. V cross R hat gives us the velocity which points this way. V cross R hat gives us the magnetic field which points down this way. So remember, B has to be perpendicular to R hat, so it's going to be a tangent right here, so it's got to be perpendicular because it's a cross product. Okay, let's do one more. Let's come down here. If we wanted the magnetic field here, that's R, this is R hat. V cross R hat gives us B. This time it points straight down. So what you'll see is that your magnetic field, no matter where you are, it's always perpendicular to the radius. That's a circle. So the magnetic field lines around a moving charge make circles around a moving charge. So we can draw those circles. Look like this, and we see that the circles are coming around in this direction, so you can put your arrows on your circle. Okay, so the conclusions, we see that B is a circle around the charge. B is a tangent to the circle at any one point. The magnitude of the magnetic field is given by the magnitude of the Biot-Savart law. We get our direction from the right-hand rule, and our B is perpendicular to V, and our B is perpendicular to R hat. Okay, so we can map out those magnetic field lines just like we did the electric field lines. Okay, any questions? So the next slide, if you downloaded the notes, is just 3 moving charge. These are in or out of the page. Draw the magnetic field lines around them. I'll post those solutions so you can just check to see that you know the answers. So let's do an example. We'll kind of take our time with it because it's a little bit review and it's got a little bit of meat to it. So in our example, we've got 2 protons. They're moving parallel to the x-axis in opposite directions. So there's one down here going to the right, there's one up here going to the left. Both protons, so they're both positive charges. They're both moving at the same speed, and that speed is slow compared to the speed of light, so it's less than c. At the instant shown, so when they're right on top of each other, separated by a distance r, find the electric and magnetic forces on the upper proton and compare how big those forces are. So there's a lot going on in this problem. Okay, we want to find the force is due to the field, so we're going to have to figure out those fields, then calculate the forces. So let's label our charges Q1 and Q2, just so we don't have much trouble with notation. I'll call the lower one Q1, the upper one Q2. I'm going to start by finding the electric force. So I'll start with the electric force. We know that electric force is charge times electric field. So let's make sure we know what we have to put in for each of these values. This is the electric force on the upper proton, on Q2. That means it's the charge Q2 times the electric field that Q2 is sitting in. So it's in an electric field. Where does that electric field come from? It's made by Q1. Okay, so Q1 makes an electric field. Because it makes a field, Q2 feels a force. So this is the field made by Q1. Let's see, what we know about electric fields is that they point out of a positive. So Q1, I could draw the electric field lines everywhere. I'm not going to draw them everywhere just because it'll mess up the whole picture. But the electric field at point Q2 points away from Q1. So there's my electric field. made by Q1 at the position of Q2. Okay, we know how to find that electric field. It's just KQ1 over R squared, multiply by Q2, and then we're good to go. So my value of Q2, it's a proton, so it has a charge of plus E. My electric field made by Q1 is K times the magnitude of charge Q1, that's E, divided by the distance between them squared. It's a vector. The direction of the electric field points straight up, so it's the J hat direction. So my electric force is equal to K times E squared over R squared J hat. At this step, you might remember that K is 1 over 4 pi epsilon naught over R squared J hat. So there's our electric force. So that was a review from our electric forces chapter. Next, we also want to find the magnetic force. So for magnetic force, we're going to remember that FB is QV cross B. What does the B come from? That's a magnetic field. That's our new bit. That's the magnetic field made by this moving charge. Okay. So next we want to find the magnetic force. So FB equals QV cross B. This is the magnetic force on Q2. That means we're using charge Q2 here. We feel a magnetic force on a charge moving in a magnetic field. So this is the velocity of Q2. It's in an external magnetic field, and that external magnetic field is made by Q1. Okay, so there's all of our bits labeled just to make sure we understand all what pieces go in there. And the reason Q1 is making a magnetic field is because it moves. Okay, if Q1 stopped moving, or Q2 stopped moving, it wouldn't be a magnetic force there. Okay, so let's think about all the things we want to put into this equation. Q2 is the charge of a proton, so plus of the fundamental charge. The velocity of Q2 is going to the left, so it's minus V times I hat. So now V is the magnitude of the velocity. We don't know what it is. We just know it's small compared to the speed of light. The size of the magnetic field is mu naught over 4 pi times the magnitude of charge 1 times V times sine theta divided by R squared. So this sine theta here, theta is the angle between V and R hat. So let's make sure we understand what the direction of that magnetic field vector is going to be. So we're trying to find the magnetic field at charge 2. So there's our R vector. R hat points along that R direction. This velocity is the velocity of Q1. Because that magnetic field is made by Q1 because it's moving with a velocity V. So let's see what this tells us about the direction of the magnetic field. We put our thumb in the direction of V, our index finger in the direction of R hat, and our extended middle finger tells us the direction of the magnetic field at Q2. That's pointing out of the page, which is the positive Z direction. So our B vector is mu naught over 4 pi times E times V divided by R squared. Our theta is our angle between V and R hat, that's 90 degrees, so times sine of 90, which is just 1. And that points out of the page, K hat. Okay, everything good? So there's lots of steps to this problem. There's a lot to think about. Let's start putting it all together, because now we have everything to put in our equation. So our magnetic force is our charge Q2, that's E, times the velocity, minus V I hat, times the field made by charge 1, mu naught over 4 pi E V over R squared K hat. So there's everything put in. Let's haul all of the numbers to the front, and let's leave the unit vectors to the end. So I get minus, let's see, mu naught times E squared times V squared over 4 pi R squared. So mu naught, 2 E's, 2 V's, a minus sign of 4 pi R squared. I cross K hat. I cross K is equal to negative J. So our magnetic force, FB, is equal to mu naught times E squared, V squared, 4 pi R squared, J hat. So the magnetic force also points up. So both of those forces point up. Okay, any questions? So if we had something like this, right at this moment, there would be a force starting to push that kind of upwards, making it start to move upwards. So that's part A of the problem, find those two forces. Part B is compare the magnitudes. I think this is kind of neat, because it's a little bit difficult to get a sense of whether a magnetic force and an electric force, which one's bigger and which one's smaller. So just looking at those equations, maybe you can't tell right off the bat. Like you've got E squared over R in both of them, 4 pi in both of them, but you've got epsilon naught here, mu naught here. You've got a V squared here and no V up here. So it's kind of hard to tell what the size of those forces are going to be. So to compare the two forces, let's divide them and see what we get for a ratio. So compare. I'm going to do the magnitude of the magnetic force divided by the magnitude of the electric force. It wouldn't matter if you did FE over FB. We're just finding the ratio so that we can say which one's bigger and which one's smaller. So the magnitude of the magnetic force is mu naught E squared V squared over 4 pi R squared. The magnitude of the electric force is this one here, 1 over 4 pi epsilon naught E squared over R squared. So there's our ratio comparing them. Let's see what cancels. So we've got 4 pi in the denominator of both of them. We've got R squared in the denominator of both. E squared's in the numerator of both, so they cancel. Epsilon naught is the denominator of the denominator, so this is the same as mu naught times epsilon naught times V squared. Okay, we're getting closer. If you're doing physics 2750, this right here might ring a bell, otherwise it might not. So something we know, and I think this is sort of a really neat trick of the universe, is that c, the speed of light, is 1 divided by the square root of mu naught epsilon naught. That was one of the ways that Maxwell figured out that light was a wave, just by putting all this stuff together. So mu naught epsilon naught is 1 over c squared. So that tells us that has to be a lot less than 1, because remember we said that V was pretty small compared to C. So then our conclusion is that FB is a lot smaller than our electric force. Okay, any questions? Quite done? So the Biot-Savart law gives us the magnetic field made from a moving charge. We know that the direction of the magnetic fields around that moving charge is going to be circles. That's shown in this diagram right here. We also know that if a charge Q moves along a wire, that's the same thing as current. So we're going to take our Biot-Savart law and see if we can write it in terms of current, because we know moving charges are the same thing as current. So moving charges would be moving along a wire. So let's draw a length of wire. So here's some piece of wire. A little bit of charge Q can move some distance for some displacement ds along that wire. So there's a little bit of distance, or a little bit of displacement, I'll say, ds along the wire. So some little bit of charge will move along that path of the wire. So ds, the definition of ds, is the segment of the path along which the charge moves. It has the same direction as the current. So our little bit of charge, or our charge q, is going to move along this little path, and it's going to take an amount of time that we'll call dt. So we'll put that bit down next. So charge q moves distance ds in an amount of time dt. And because this is a charge and it's moving, it makes a small amount of magnetic field. So what we're doing here is building to an expression where we'll be able to incorporate the current. We'd like to use our Biot-Savart law. So let's think about this QV cross R hat, because that's all the vector business, and that's where charge comes in. So let's think about what that's going to tell us. So in our Biot-Savart law, mu naught 4 pi and r, those aren't very interesting. It's the QV cross R hat we have to worry about. QV cross R hat, V means the velocity of the charge. The velocity would be the displacement over time. So it's Q ds over dt cross R hat. And then here's where we recognize that Q over dt, that's our current. So charge flowing over an amount of time is equal to the current. So this is equal to current I ds cross R hat. Okay, that takes care of this part of the numerator. So let's put this in our Biot-Savart law, and let's see what we can get. So now our little bit of field, dB, is going to be mu naught over 4 pi times QV cross R hat, which we just said was I ds cross R hat, and then that has to be divided by R squared. So that's the little bit of field made as the charge moves that little distance. If we'd like to find the total field, then we have to take all the little bits added up. So then that gives us that our net magnetic field made by a charge moving along a wire, or a current, would be the sum of all those little bits of field, or the integral of mu naught over 4 pi I ds cross R hat over R squared. So this gives us the magnetic field around a current carrying wire. If we wanted to think about the direction, and we'll just kind of put some more details on the next slide. This magnetic field, this is just an alternate description, right? Including the current is just another way to say moving charge. If moving charge makes circles around the charge for our magnetic field, then the magnetic field around wires are also going to be circles, because the current is just the moving charge. So moving charge makes a circular field, whether it's a charge by itself or a charge moving on a wire. But we'll look at those details now on the next slide. So what does the magnetic field around a current carrying wire look like? We definitely know it's going to make circles around the wire. We know that those are going to have a specific orientation. And we also know, and we are going to get around to proving, that the strength of that magnetic field is proportional to 1 over the distance between our point and our wire. So we are going to come around to choosing this. So the magnetic field around the wire, so this is just a current carrying wire. Let's say it's got current coming up out of the page. So current looks like this. This is a picture that shows iron filings tracing out the magnetic fields, magnetic field lines. So they would look something like this if you drew them. We can find the direction of the magnetic field at any point, just like we did on the previous part. So we pick some little bit of path, ds. So let's pick that down here. There's our ds, that's coming upwards. If we want the magnetic field, say right here, we can draw our r vector and our r hat vector. ds cross r hat gives us a magnetic field that comes out this way, right? So ds is up, r is this way. This is a 3D picture, so this is kind of hard to draw. There's my best effort. You can do that at any point, and we would see that the field lines come around this way. It can be easier to take a 2D view versus a 3D view. So if we decided to look down on our wire instead, we would see the current coming out at us. If we wanted to plot the magnetic fields in a 2D way, we do the same thing. The current's coming towards us, so that's our ds is towards us. If we wanted to find the magnetic field, say up here at the top, then we draw the r vector, draw the r hat vector. ds is out of the page towards us, that's the way the current is moving. R is up, and our magnetic field points towards the left. So there's the magnetic field right there, perpendicular here. So our magnetic field makes circles around the wire. It's a tangent to the circle at any point. Which means it's perpendicular to R at any point. There's a simplified version of this right-hand rule. And if you did physics in high school, this is probably the one you learned. It was you put your thumb in the direction of current, you make a circle with your fingers, and those curved fingers show the orientation of the path. It's the same rule. You get it from doing ds cross r hat. It's the same way of giving, right? So it's one rule, just simplified. So that's the same as what we were talking about for the magnetic moment. If the current comes up out of the page, the circle with your fingers comes around counterclockwise. If the current goes down into the page, then your fingers are coming around clockwise. So it's another way to do the same rule. Okay, questions here? Okay, one neat application. One question I don't get a lot, but sort of pops into my head, is why does the Earth even have a magnetic field, right? Doesn't that feel weird that a planet has a magnetic field? It acts like a big bar magnet. And some planets do have magnetic fields, not all of them. Jupiter also does. So it's not super well understood, right? There's still lots to learn about magnetic fields around planets. But basically, some planets have a molten core. So like the Earth has iron and nickel, and it's so hot inside the core of the planet that that's all liquefied and it's moving around. We have these hot moving metals. They transport currents all around the center of the Earth. So inside the center of the Earth, we have all of these moving currents. All of those moving currents make the magnetic field around the Earth. So that's kind of an idea about it. So if you study the magnetic fields and compare them to that of other planets, you can figure out some stuff about the nature of those planets. It's why it's interesting for astronomers to study. Yeah?
Yeah, so does the movement of the molten rocks have anything to do with charges?
Yeah, well, it transports the charge around, so it's all connected, right? So the charges are moving within those liquid rocks.
So are the rocks have they been broken into their ions and electrons, something like that?
It's probably not broken down into the ions. It's probably more like how ice melts into water. It's probably more like that, right? So you just get flowing iron and nickel and stuff. But honestly, I don't know lots about it. I'll see if I can find something interesting, right? Find out a bit more. Yeah.
Jupiter, forgive me if I'm wrong, it's a gas giant, isn't it?
I don't wanna commit, yeah, I think it is.
So, what would create the magnetic charge?
Yeah,
for
there's a good
gas?
question. I guess it's the moving gases, and maybe they ionize, like you're saying, right? Yeah. But there's definitely stuff in there that, you know, that we've got moving charges around. If I had to guess, yeah, maybe the gas ionizes in there, and that would be like a little bit like a plasma, so then that's all moving around. Yeah, okay. I'll try and figure some more stuff out, and then anybody who's interested. If you haven't picked your research topic yet, there's a little bit you could just learn a little bit about, and you could present it on. That would certainly be applicable. Okay, so now, any more questions? Okay. Now let's do sort of the classic example for this course, which is find the magnetic field around a long line of current. If you did physics 1021 or 1051, you were probably just given the answer of mu naught I over 2 pi r. We'll go through the process of seeing where that comes from. So we're going to start with our Biot-Savart law, and we're going to apply this to a long line of charge. I haven't drawn a very long one here, but this is really, really long, sort of approximating infinity. Okay, so it's really long. So let's think about some of our things we're interested in. We'd like to find the magnetic field at point P. So I'll label my point P up here. My wire needs to carry some current. I'll just somewhat arbitrarily say that that's going to the left. So there's my current I. The direction of my magnetic field. So you put your thumb in the direction of current, you curl your fingers. What are your fingers doing at point P? They're going into the page. So the direction of the magnetic field at point P would be into the page. We can draw that. That comes from the right-hand rule. We know those magnetic fields are big circles, but at this point specifically, it's going into the page. So let's start thinking about our Biot-Savart law. So the magnitude of the magnetic field, because we've already dealt with the direction, is the integral of mu naught over 4 pi times the current times the magnitude of ds cross r hat over r squared. Okay, let's label a few more things on our picture. So ds is a little element of the wire. It's the displacement that the piece of charge moves along. So there's our ds coming from here to here. R is the vector between S and our point P. So the magnitude of that is R. And r hat would be the unit vector pointing towards P. So we're just labeling our picture like we've done. Magnitude of ds cross r hat, let's deal with that one next. That's going to be the magnitude of ds times the magnitude of r hat times the magnitude of the angle between them. So the angle between them, there's our ds, there's our r hat, there's our theta right there. The magnitude of ds, we can call ds just for the size. ds is a little piece along a horizontal rod. ds is a little bit of thickness in the x direction, so ds is the same as dx. The magnitude of r hat, remember that's a unit vector, so it just has a magnitude of 1. For sine theta, let's think about a little bit of geometry. My distance along the y-axis, I can call y. My distance along the x-axis, that can be x. Sine theta is opposite over hypotenuse, or y over r. So let's put all of these things in our expression for the magnetic field. So the magnitude of our field is the integral mu naught over 4 pi times I times dx times y over r squared times r cubed. Okay, so I just substituted in that the magnitude of ds cross r hat was dx times y over r. So far, so good? I've got an R here, so let's make sure I know what R stands for. R is the hypotenuse of a right angled triangle. So R squared is x squared plus y squared. R is the square root of x squared plus y squared, or x squared plus y squared to the 1/2. I've got an R cubed here, so R cubed is x squared plus y squared to the 1/2 cubed, or to the 3/2. And that was a little bit of geometry we saw in our electric fields as well. So now this can come over here, and we'll get ready to integrate. So this is mu naught times I over 4 pi times dx times y over x squared plus y squared to the 3/2. I can take all of my constants out front, and a lot of that stuff is constant. So mu naught is constant, I is constant. We're going to say y is constant. We're not moving it around in the middle of the problem. Divided by 4 pi dx over x squared plus y squared to the 3/2. So there's our integral. We need limits on our integral. When we integrate, we will integrate from one end of the rod to the other. So one end of the rod will be over here. The other end of the rod will be over here. I'm going to say that this end of the rod is at minus a, and this end of the rod is at plus a, and overall our length equals 2a. Okay, so it goes from minus a to plus a, and I picked my point right in the middle above the wire. So the limits of my integral are from minus a to plus a. Equals look up integrals. Again, if you like to integrate, no problem, you're welcome to work that out, but that's not something I would ask of you on a test. I would give you the table of integrals so you could look it up. If you look up that integral, what we get for our result is mu naught times I times y divided by 4 pi times 1 over y squared x over square root of x squared plus y squared, evaluated at a and minus a. So there's our integral after we look it up. I am keeping an eye on the time. I won't keep you over time. So we want to put in a and minus a for our x. We notice we've got a y up here and a y squared down here. So this is mu naught times I over 4 pi y. A over the square root of a squared plus y squared minus a square root of a squared plus y squared. Let's see, minus times a minus gives us a plus. So there's two of these guys. 2 mu naught I, a, 4 pi y, square root a squared plus y squared. Okay, any questions to here? So now let's deal with the fact that we want a long wire. If you had, say, a 1 meter long wire, you could totally just put your numbers in here and calculate it. So you could definitely put your numbers in it. If we have a long wire, what that means is that A is going to be a lot bigger than Y, so it's a lot longer than we are distance to the point we're calculating, so that's a good approximation. And we can think of A as kind of getting close to infinity, so A is getting close to long. If A is approaching infinity, then A squared plus Y squared is about equal to the square root of A squared, which is equal to A. Okay, so there's an approximation we can do. So then our B is about equal to 2 into 4 gives us a half. So mu naught I over 2 pi y, A over A. B is about equal to mu naught I over 2 pi y. This is the expression we're probably familiar with from high school or 1051. Just the one last thing is typically we use R here instead of Y. So B is equal to mu naught I over 2 pi R. And you can get the direction of those magnetic fields using the right-hand rule. So your thumb goes with your current, your B makes the big circles, and your B at any specific point is a tangent. What we're gonna get into next day is just doing some concrete examples where we'll draw those fields and calculate the magnitudes of those.